Okay, so in this particular case, moment of inertia, so if I have a bunch of masses around here, moment of inertia is the variance of the location of the masses. So roughly speaking, I am going to compute xi squared mi divided by summation of mi, yi squared mi divided by summation of mi, and so on. Okay, so that's how I compute moments of inertia. Instead of doing xi mi, I'm going to do xi squared mi. In terms of computations, calculus, everything, I'll just have a little bit more complicated integration, but no big deal. Okay, so here it is. The moment of inertia around the x-axis for a planar region is summation of yi squared mi. Moment of inertia around the y-axis is summation of xi squared mi. So it tells you how much variance is there around the y-axis and how much variance is there around the x-axis. That's what it means, right? So you cannot, it's not just about masses, you can also do the same thing with areas. So area moment of inertia around the x-axis is summation of yi squared ai, and area moment of inertia about the y-axis is summation of xi squared ai. Okay, and notice I don't have to divide by area or anything, it's just moment of inertia. Okay, that's all there is to it. Now of course, if you want to do integration, it's the same thing, integration from left to right, integral from bottom to top of x squared dx dy dx is called I y, and then ix is integral left to right, integral bottom to top of y squared dy dx. Okay, this is actually a fairly easy integral. Oops. This is actually a fairly easy integral because this equals integral left to right of x squared y between bottom and top dx, and this is integral left to right of y cubed over 3 bottom to top dx. That's all. Hey, there's nothing much to it. You know, in one step you can convert it into an integral that's local, but I just want to show you what it looks like. Okay, this formula is a little bit more useful than this one because it directly connects you to the definition of moment of inertia. This doesn't look very obvious, but if you start from here, you can always get here. Okay, let's look at an example. Okay, so now I'm looking at this example. So again, let's look at this thing, and I'm going to say left equals x equal to this is the left, x equal to -2 is a line, that's that side. Right equals x equal to 0, that's this one. Bottom is y equal to 0, that's this line. And then top is y equal to x over 4 times x minus 8, that's this line. If you look at this thing, this is left, right, bottom, top. Okay, now we are in business. Let's compute ixx, or ix equals integral left to right, so x equal to -2 to 0, bottom to top y equal to 0 to x over 4 times x minus 8 of, remember it's ix, so I have to do y squared dy dx. If you compute this thing, this will turn out to be integral x equal to -2 to 0 of x over 4 x minus 8 this whole thing cubed over 3 dx. You got to expand this and integrate it out. If you integrate this whole thing out, you will get 1942 over 105. Iy will be integral x equal to minus 2 to 0, integral y equal to 0 to x over 4 x minus 8 of x squared dy dx, which if you integrate it, it will turn out to be 48 over 5. That's how I compute. That's all. Easy, no? I wanted to understand that if you know a little bit about double integrals, these things are trivial. There's nothing to it. If you don't know, better learn it now. Okay? That's how I compute Ixx and Iyy and all of these things. It's a fairly straightforward deal. Of course, as with the other one, what if you want to do something for a composite area?